Always a bit of discrepancy here. I am a little bit surprised to see Harry Potter so close to the top. I feel like even though Harry Potter was huge for my upbringing, it's kind of dropped off in favor over the last few years. I'm surprised that Harry Potter beat out Percy Jackson. That's never happened before with this generation. So kudos to you guys. Don't forget, I have attendance open. It looks like more of you have had more success with it today than you did on Thursday or Tuesday, but please keep that in mind to try to be aware of your attendance. I think we're ready to get started. So in the last class period, we discussed electric fields, kind of how they related to the electric force on a positive test charge. We talked about electric field lines, which kind of was a map that related how strong the electric field and in what direction it was pointed. And so today, what we are chiefly concerned about is, okay, now that we have the concept of what an electric field is, we need to discuss what does an electric field do? How does it work? How does it behave? What is it going to do when charges are brought into that region within the electric field? So the first thing is, I hope that you haven't forgotten this already from Physics 1, but there was this guy named Isaac Newton. He had an apple drop on his head and had an epiphany, a little bit of a glossing over the details of that story, but all that comes down to the simple idea that he was able to relate that forces, masses, and accelerations are all related to one another. And he stuck this into a single equation and called it, well, now it's called Newton's second law, and that is that force is equal to mass times acceleration. If you want to know how much force, net force, is acting on an object, you know its mass, you know its acceleration, that's how you calculate its force. Or specifically, what we're going to do in this situation is we want to know how a particle in an electric field is accelerated. So the acceleration is going to be the net force over the mass. And we said that last time, for a charged particle in the presence of an electric field, the net force is just the charge times the electric field. And so the acceleration of a charged particle in an electric field is equal to the charge itself times the electric field strength divided by the mass of the particle. And so you can even see right off the bat, if you take a look at this equation, we know that protons and electrons have the same charge. They both have, well, with the plus or minus, the same charge. An electron has minus elementary charge, a proton has plus elementary charge, but they have two very different masses. The proton is about 10,000 times more massive than the electron. And so if you take that into consideration, same charge dropped into the same electric field, but now the proton is much more massive than the electron, the proton's acceleration is going to be much lower than the electron's acceleration, just as a general rule of thumb in the same electric field. Now, the other thing that an electric field will do is it can exert a torque on something, say, like a dipole. And so what we want to do first is define even what a dipole is. A dipole, you may recall from chemistry, a dipole is just when you have positive and negative charge that are in close interaction to one another, but are indeed separated spatially from one another. And so in this case, we have a charge, minus q, separated by a distance L from a charge plus q, and that distance L we're going to represent as a vector pointing from the negative charge toward the positive charge. And so from negative to positive charge, the distance L, if you multiply those two together, charge times vector distance there, then that is going to be our dipole moment, as it's called. Lowercase p vector, in this case, is dipole moment, not linear momentum like we learned last semester. And if you had me for last semester, you already know that even talking about what momentum is kind of a taboo topic anyway. Right? Don't hit the universe destroying button at the Large Hadron Collider. So dipole moment is charge times the distance that separates the magnitude of charges. And the reason that this is important is because now if we drop this dipole moment into, or this dipole into an electric field, then what we expect is that the electric force on the positive charge is going to be in the direction of the electric field. The electric force on the negative charge is going to be opposite the direction of the electric field. And so you get this twisting effect where you would essentially have the dipole moment, which on the screen is aligned, this way. And so if I get pulled one way to the left on the positive charge and to the right on the negative charge, then you're going to get that this dipole is going to want to tip over such that as it tips over towards being parallel to the field, we would say that the rotation that is caused by that has to come from a torque, right? Because we said that when we apply Newton's laws to rotational mechanics, what you end up getting is that, okay, torque is equal to I alpha, if you remember that one. Tau is equal to I alpha, the moment of inertia times the angular acceleration. And so what's interesting about this is while it passes through the equilibrium position, while it passes through the lowest energy state, the unfortunate thing is, maybe not unfortunate, but the resulting motion is that it's going to have angular velocity as it passes through the low energy point, and so it's going to pass right through it. And so what's going to happen is this dipole moment is going to act like a pendulum as it rocks back and forth, trying to align to the electric field, passing alignment, and then trying to realign to the electric field. And so you kind of get this pseudo simple harmonic motion. The torque itself, pause. By the way, if you don't remember, I think we discussed this when we discussed torques to begin with, that operator between P and E is the cross product. If you need kind of a revamp on what the cross product is, look in chapter, I think 8 or 9 in your textbook, or come talk to me about it during office hours, but that's a cross product between P and E. So we can take if the torque rotates the dipole through an angle d theta, then the differential work done, just like we did in the chapter on torque, is going to be minus tau times d theta. And the torque, or at least the magnitude of the torque, which is taken as the magnitude of the cross product, is going to be P times E times sine theta d theta. Well, since this is a conservative force acting here, then we can relate the amount of differential work done to the differential amount of potential energy change. And we can integrate, and the main takeaway here is that we can integrate to get that the potential energy is equal to minus PE times the cosine of theta, where theta is the angle between the electric field and the dipole moment here, plus some arbitrary constant of integration. And if we set the potential energy at 90 degrees, where the cosine is 0, if we set the potential energy at 90 degrees equal to 0, then the constant has to be equal to 0 at that point. And so you get that U is equal to minus P times E times cosine of theta. And if you know anything about P times E cosine of theta, that is the magnitude form of taking the dot product, which is how we define our final form for electric potential energy of a dipole, is equal to the dot product between the dipole moment and the electric field. So the torque was P crossed into E. The potential energy is, oh, and you might notice here, I missed it again as I was revising my slides today. There should be a negative sign right here over top the mouse. But the potential energy of a dipole in an electric field is minus the dipole moment dotted into the electric field. Okay? Yes, right here.
In the equation what we're proving, are those P and E's, is that the magnitude of the torque and magnitude
The P everywhere before the mouse is the magnitude of the dipole moment. So the magnitude of distance of separation times the charge that is separated. Same thing with the electric field. Up until we get to where the mouse is, we're just talking about the magnitude of the electric field, not the electric field as a vector. Yep. Any other questions? So let's look at really quickly, before we move on, where we have the torque on this dipole moment. Specifically, it looks like OneNote was updated yesterday, by the way, so we'll see how this new update works. But if we're mapping potential energy as a function of angle, which I guess what I need to do is actually write it like so. So this is theta, and this is potential energy U. We said that potential energy U is equal to minus P dotted into U, dotted into E, or that was equal to minus PE cosine theta as our potential energy. And so what I'm trying to get you to see is the potential energy function is therefore going to look something like this right here. Where we've got that nice cosine function. And so we get a minimum down here at, actually let me switch colors one more time. We get a minimum right here at 90 degrees, at 0 degrees, excuse me. We get a minimum here at 0 degrees. At 90 degrees, our potential energy is 0. And at 180 degrees, we get a maximum. And same thing here. This would be minus 90 degrees and then minus 180 degrees. And so we can again infer the same type of motion that I was just talking about before when I was talking about the torques, when this thing is going to want to oscillate back and forth. That is, if I drop in here, can't change the type of, that's frustrating. If I drop in the dipole at this orientation, say between 45 and 90 degrees, what's going to happen is, so in this case, we've got the electric field is going to look something like this, and then the dipole is going to look like minus plus, something like this. So this would be the case that I've got drawn here. What's going to happen is I'm going to want to go to a lower energy state. So I'm going to want to change this, this setup. Let's see if I can grab just this. Yeah. I'm going to want to change to where at 0 degrees, my dipole looks something like this. But since I still have kinetic energy as I pass through this point, I'm going to start rising up the ramp over here. And so you're going to get something that starts happening that looks like this, where you start oscillating back and forth along that electric field line. And so a classic question, again, that I want to ask based on Phys 1 is, again, what tends to happen when I see students working on problems such as this one is, okay, I have the particle now up here at 90 degrees. Let's say it's oriented such like this right here. The potential energy is 0, according to how we define the potential energy. Does the particle start to oscillate or reorient itself or not? If it does, why? If it doesn't, why not? The potential energy is 0. Right up here. So total energy, so we could have that if it starts at rest right here, right? The total energy is defined as E is equal to U plus T, where T is the kinetic energy, right? So if it starts from rest, it has 0 kinetic energy and 0 potential energy. It has 0 mechanical energy right here. So does it oscillate or not? It does. Why? You're right. Andrew? Okay, so if we think just in terms of the forces, yeah, there's going to be an unbalance of rotational forces here. These are each of the forces acting because the force on the positive charge is in the direction of E. The force on the negative charge is opposite the direction of E. So yes, in terms of thinking of the forces, we do get oscillation, but why do we get oscillation if the potential energy is 0? Oh, ask your question.
What happens if it's at 0 then? Isn't that what it's trying to get to? Is when the angle is at 0?
So yes, it's trying to get to an angle of 0. It's trying to get to this point down here. Or if I take each of these, right, it's trying to get to this point. But how can it still get to that point if the potential energy is 0? Maybe the question is better asked as, does it matter what the potential energy at any single point is? No, it doesn't. What matters? Okay, so energy is conserved, you're right. Yes. Okay, so what matters is how the potential energy can change. Can the potential energy decrease? Yes, it can. When you're at 90 degrees, even though the potential energy is at 0, the potential energy can decrease. Nature seeks to decrease potential energy, and so it doesn't matter what the potential energy is, even if it's 0, the fact that it can decrease, it's going to try to make the potential energy decrease. And what happens when the potential energy decreases? It goes negative, which means that the kinetic energy has to go positive. Right? So the total energy will stay at 0, but what's happening is I'm decreasing potential energy to raise my kinetic energy. I'm decreasing the amount of energy stored in the electrical system, and I'm converting it into energy of motion, rotational motion. But then I start climbing back up this hill here to get to this point, and I start slowing down, so I'm converting more and more of my kinetic energy into potential energy, and the process starts all over, and I just start tipping back and forth like so. So remember, classic mistake in Physics 2, even though I tried to drill this into you in Physics 1, classic mistake even still in Physics 2 is you state, well, the potential energy is 0, no motion occurs. See it all the time on exams. But don't forget, we don't care about how potential energy is at one point. We care about how it can change.
Does it do this infinitely, or does it stop at some point?
Yeah. So here's the question. Does it do this infinitely, indefinitely, or does it stop at some point? In our perfect little world that I have derived here on the screen, it's going to do this infinitely. There's nowhere else for the energy to drain off to. So either it's going to be potential energy, kinetic energy, or some combination thereof. In a realistic situation, you've got some sort of air resistance, you've got some sort of drag effect, you've got something that is going to remove energy from the system. And so what happens in that case? It slows down, but where does it slow down to? Like, where does it stop? Yes, when it's parallel to the field. So if I can drain energy off of this system slowly over time, then what's going to happen is I'm going to get very big oscillations. They're going to start slowing down, until eventually my system comes to rest right here at this point. Yes. Good question. Maggie?
So 0 degrees is its equilibrium.
0 degrees is equilibrium. Yes. Why? Okay, yes, so I've got as much pull, I've got equilibrium here if I'm thinking in terms of my forces, right? So I've got this scenario where I've got as much pull to the left and to the right, it's not going to cause my system to rotate. But let's think in terms of the energy here. How, question or answer? Okay, question.
If potential energy is zero, does not mean that it's maximum kinetic.
Not necessarily. The question was, if potential energy is zero, does that mean we're at maximum kinetic energy? Another situation could occur where instead of releasing this particle from rest at potential energy to zero, I could have given it an initial kick from that point. So that means I would go up this ramp and then start falling back down again. And so my maximum potential kinetic energy only occurs at my minimum of my potential energy. And I think that gets to what I was trying to ask Maggie and the rest of the class here is, okay, it comes to rest right here at the minimum. And why is it important that it comes to rest at the minimum? Because we said that we seek to decrease potential energy. And I can no longer decrease my potential energy, right? Like if I'm at the minimum, I'm as low as I can go. I can't go any lower. So if I can't go any lower, there's no more change. Another way to think about this, the way that we defined this, at least in one dimension, we said that the force in, say, the x direction is equal to minus the derivative of the potential energy with respect to its position, right? Now, we're talking angles here, but the concept is still the same. So your force, your motion, the subsequent motion depends on the derivative of the potential energy, not the potential energy of itself. What's the potential energy at the minimum? What's the derivative or the slope at the minimum? Zero. Right. Zero slope means zero change. Whew. So many wonderful concepts in physics just brought together from one simple example. And this is where I was a student once too. I remember thinking that it was crazy that we had prereqs and all this other stuff, but I promise you, you have prereqs for a reason. Please don't brain dump. Hopefully you haven't done that already over Christmas. Please don't brain dump all the stuff that you learned in Phys 1. We're going to keep using this stuff over and over and over again. It all builds on one another. And you're thinking, I'm just ready to be done with this, and I still have a semester left to go, or 2 semesters if you have to take 113. I get it. Don't brain dump. Okay. Got to regather my thoughts here, see where we are. I think, if I remember correctly, how y'all feeling at this point before we move into some problems? All right, so the majority of you who put the second or third answer of I'm getting there, I'm so lost. Any specific questions that I can answer about electric fields and forces and potential energy before we jump into problems? All right, well then let's dive in. That's wrong day. Here we go. Oh, by the way, if you didn't read my announcement ahead of time or you just saw the part about attendance, I have now put the blank problem sets on Canvas. If you want to look at them ahead of time to try to give them a shot yourselves, or if you just want to have them downloaded if you use a tablet or something like that. just so that way you have the reference point for what questions we're doing to work it on here, whatever you want to do. The electric field near the surface of the Earth points downward and has a magnitude of 150 newtons per coulomb. So we've got this, we've got an electric field that we're assuming, based on no other reason to assume otherwise, that is a uniform electric field. Compare the magnitude of the upward electrical force on an electron with the magnitude of the gravitational force on the electron. Okay, so we have resting inside of this field here an electron. All right, let's start with the easy question. Physics 1, right? In what direction is the gravitational force? Yes, downward, vertically downward towards the ground. So I've got F sub g is vertically downward, and F sub g, at least in magnitude, is going to be, how would I calculate that? Yeah, since we're close to the surface of the Earth, we're going to not use the Newtonian formulation. We're just going to say it's equal to mg, right? And the mass of an electron, I think, is 9.11 times 10 to the minus 31. Let me pull up my notes. 9.11 times 10 to the minus 31 kilograms. Times gravity, 9.81 meters per second squared. And in that case, you get a force that is 8.93 times 10 to the 30, minus 30, newtons. So a really, really tiny insignificant force. It would be to the negative 31. That's twice that you've called me out on that. I'll go with my standard response. It's just to keep you guys on your toes. I only make mistakes on purpose, right? Wrong. All right, in what direction is the electric force acting on this? So we got to vote for down. Remember that the electric force is in the direction, well, actually, let me write it out as a vector. Electric force is equal to charge times electric field. So the electric field is down, so since the charge is negative, we have to flip the direction. So the electric force is upward in this case. Yes. And I can't draw this with appropriate magnitude, as you'll find out here, but the electric force, as we're about to find, is going to be much, much greater on this electron than the gravitational force is. So the electric force is going to be Q times E. Since we're just talking about magnitude and not the vector, I'm just going to say that we're going to be taking the absolute value of the charge, so that's little e times big E, or E. So that's 1.602 times 10 to the minus 19 coulombs times an electric field strength of 150 newtons. And that comes out to be 2.4 times 10 to the minus, 17 newtons acting upward on this electron. 13 orders of magnitude stronger, so over a trillion times stronger. Specifically, let's see, I think that's all they're really asking for here, is just asking you to show that the electric force is much, much greater than the gravitational force. Maggie and then Bill.
The electric force is going to be a lot greater than the gravitational just because it's on such a smaller scale, right?
So her question was, the electric force is so much stronger than the gravitational force because we're talking about scale. I think a good answer to your question is the frustrating one, yes and no, right? So we're about to do this one with the ping pong ball. And what we're going to find, though, is that, okay, now let's take something that is macro in scale, like something that we can hold in our hand. The crazy thing that we're going to find in this next part is you only have to put a very tiny amount of charge on the ping pong ball to get it to go up. So we're talking about grams, right? Well, the solution that we're going to find is going to be microcoulombs. So I have to only put 10 to the minus 6 coulombs on here, whereas I've only got 10 to the 0 grams. Okay, so yeah, we're talking about scale, so the mass of the electron is not significant enough to counterbalance how much charge it has. But even still, it only takes a tiny amount of charge to counterbalance any amount of mass. And so to get into your question, if you look at the relative strengths of the 4 fundamental forces in the universe, the strongest force in the universe, unsurprisingly, is the strong force. That's why we call it that. The next strongest force is electromagnetic. The next strongest force is the nuclear weak force. And then the least strong force is the gravitational force. It requires a ton of mass for gravity to have any bearing on your problem whatsoever. So what we're forgetting when we're just talking about ping pong balls and electrons is that you get pretty strong forces if we have 2 microcoulomb charged ping pong balls. Like ping pong balls. You get strong repulsion. But what are we leaving out of the picture to have any measurable gravitational effect in this problem to begin with at all? You're leaving out the fact that there are 10 to the 24 kilograms underneath your feet, right? A trillion kilograms that are contributing any of the gravity to make this all possible to begin with. So that's where your frustrating yes and no question comes from.
I was wondering, like, in your equation, how do you go from Q to E?
Because this is the general variable that we tend to use for charge. And what specifically is the charge on an electron? Specifically, the charge on an electron is minus an elementary charge.
Wow, and that's one of the numbers you just have to remember.
Yes, it's on your equation sheet, right? The elementary charge is one of the constants that's on your equation sheets.
Oh, so we'll get that.
So you'll have 1.602 times 10 to the minus 19, but it is up to you to remember that an electron has negative elementary charge and a proton has positive elementary charge. Good.
Will you also give us the mass of the, like?
Yes, mass of protons and electrons and neutrons are on there as well. Yes. Okay, so now we have a ping pong ball, right, with mass 2.7 grams, so that the electric force, we want to know the charge such that the electric force is balanced here. So now what I'm looking for instead of this is I want to know the charge such that these two forces are equal and opposite. So Fe is equal to F times the force of gravity. But we're just talking about magnitudes here. So that would be Q times E is equal to M times G, or Q is equal to mg over E. So that's 2.7 times 10 to the minus 3 kilograms times 9.8 meters per second squared Don't know why I just arbitrarily started sticking units in there. Divided by 150 newtons per coulomb. This comes out to be a magnitude of 176 microcoulombs. Now, is that a positive or negative amount of charge? Again, I was just starting here based on the magnitude. So is that a positive or negative 176 microcoulombs? It's negative, you're right. Why is it negative? Okay, so yeah, it's talking about an electric force to counterbalance gravitational force. Therefore, we need an electric force going up. And when the electric field is pointed down, the only way we get an electric force going up when the field is down is if the charge is negative. And so in this case, Q, at least in terms of, when we're not just talking about magnitude, is going to have to be negative 176 microcoulombs. Good. Okay, so gravity is pulling down, right? And to counterbalance gravity, we have to have electric force going up. And the only way we get an electric force going up when the electric field is going down is when you have a negatively charged particle. Yes, anytime the force is opposite to the field, the charge has to be negative. Negative charges go opposite the direction of electric fields. Positive charges go parallel to electric fields. Yes, if the electric field had been pointing up in this case, this would have had to have been a positively charged ping pong ball. Try playing ping pong with a positively or negatively charged ping pong ball in the Earth's electric field. Well, you'd end up getting that the ping pong ball would just go straight instead of bouncing off the table.
You got the 2.7 times 10 to the -3 by running.
Yes, the grams are not the standard SI unit of mass, kilograms are. And so I converted grams to kilograms, which would be a factor of 10 to the -3.
And for the 9.11, is that the mass of the...
That's the mass of an electron. Again, on your equation sheet. 10 to the 9.11 times 10 to the -31 kilograms. Jacob and then Grayson. The elementary charge, 1.602 times 10 to the -19 coulombs. This is E, little e. That's on your equation sheet. That might be a little bit of a stretch, but because they are vectors on each side, the way that you would get an acceleration opposite of the force is you'd have to have negative mass, which to date we still haven't found, but some people are still looking for negative mass. Basically, if there is negative mass, gravitationally speaking, that would mean that gravity would work opposite to how the electric force works, right? Where instead of opposites attracting, you would have opposites repelling in gravity. That's weird to think about. You stick a positively charged mass Earth and a negatively charged moon, and they push away from one another. Charged mass, I don't know what you'd call that. A point charge of 5 microcoulomb is located on the x-axis at x equals -3 centimeters. So here's my x-axis. Let's call this 0. I'm going to call this Q1. Q1 is here. X1 equals -3, and this is in centimeters. And I've got Q1. Then I've got at x equals 4 centimeters. equals plus 4, a charge of Q2 right here. And it's saying where should a third charge of 6 microcoulomb be placed so that the electric field at the origin is 0, right? I mean, the first question to ask yourself is the electric field at the origin already 0? Why or why? If it is, yet why? And if it's not, why not? Okay, so they're not equal distance and they're not equal charges. Specifically, maybe an easier way to think about it is Q1 is positive and Q2 is negative. So if we look at the origin right now, I have electric field lines radiate away from positive charges. So E1 is going to look something like this. And then it's going to be pointed toward negative charges. And that means that E2 is also going to be pointed to the right. So if they're both pointed to the right, two vector quantities both pointed in the same direction can never cancel each other out. So no, the electric field, just by inspection, is not 0 at the origin already. The third charge that we're trying to place here, let's call it Q3, is positive. So do we expect this positive charge to lie on the positive x-axis or the negative x-axis, and why? Positive. Why, Andrew? Oh, sorry. Positive. Why, Andrew's neighbor? Okay, yeah, so we need the charge Q3. Let's call this distance here an arbitrary distance x. We need Q3, which again is going to be positive, to be somewhere on this side of the axis, such that E3 is going to want to point to the left here. It's going to radiate away from that one. And likely it's going to have to be pretty close to the origin because it's having to counteract two things going to the right. And so it should be closer than probably 3 centimeters. So I know this feels like really slow progression of problem solving, but these are the kinds of things that I'm hoping that when you're doing your homework and when you're doing the pre-lectures, these are the kinds of things that I'm hoping you're storing in the back of your mind, because if you get an answer at the end of all of this, and the answer happens to be negative, or happens to be 10 centimeters, then you can tell yourself, I bet something went wrong. This doesn't make sense. Does anybody remember off the top of your head, how do you calculate specifically the electric field of a point charge? This was from last lecture on Tuesday. Sorry, what? I didn't hear where that was from. Distance squared, yes. So just the magnitude of the electric field due to a point charge is k, q, over distance squared. Good. And so, what I would end up getting here, let's see, how can I think about this? We've got E. Oh, yeah, okay. The vector form of this is equal to k q over r squared times r hat. There it is. That's what I was trying to think of. Now I go through that to state, okay, we want the electric field at the origin to be 0. Actually, let me write it out this way. The electric field at x equals 0, we want to be equal to 0, right? Well, that would be the sum of the contribution from charges 1, 2, and 3. So from charge 1, I get K times Q1 over x1 squared. And then the direction, r hat here, this is r1. That's in the minus I hat direction. Right? I think I've got that written down correctly. Something. No. Sorry, I'm trying to do this differently than I did it last year just to make it explicit. Remember that the vector r always points from the charge to the point where you're measuring the electric field. And that's how it's supposed to work out better. So that would tell me that it's pointed in R1 is pointed in the plus I hat direction. You follow my reasoning here? And again, does that make sense? This whole package is going to be E1. And that tells me that E1 should be pointed to the right in the positive I hat direction, which we reasoned it should be. So, okay, that's correct. Plus the contribution K times Q2 over X2 squared. But now R2 is pointed in the minus I hat direction. Well, we said that the electric field was to the right, but according to this right here, that would tell me that the electric field is to the left. What gives? What? Q2 is negative, so a negative times a negative is going to flip it back over. So good, we've got that one pointed in the right direction. Plus, by the way, this here is E2, plus K Q3 over X3 squared. And that, again, R3 is pointed to the left. So we've got negative I hat here, but Q3 is positive, and so that would mean we'd get an electric field pointed to the left. So that is consistent as well. Yes, Maggie, and then up here. Yes, because we're solving for a zero electric field, the first and easiest thing to do would be to divide the whole equation by 0 and divide the whole equation by I hat. So we'd end up losing a K and an I hat. So good. But before we do that, Mr. Shoemaker. Yes, negative charges draw electric field lines inward, and electric field lines radiate outward from positive charges. Other questions? Yes?
What prevents this? One, right now with Q3 surplus of Q2, the right side of Q3 has an extremely strong connection with Q2. What prevents
We're not talking about the interactions between each of the charges. We're just talking about how the three existing charges interact with the origin. Good question. So yes, you're right. Q3 and Q2, if they are released from their positions, they would be attracted towards one another.
since the right side of Q2 and Q3 are really connected, what prevents left side Q2 the feedback into itself?
So if we were to map all of this out, let's solve it first, and then we can go to PhET and look at like what this would look like. And yes, you're right. You would get this bowing away effect right here at this point. You're exactly right. But let's map that out. So following Maggie's advice, we've got 0 equals all of this stuff here. The easiest thing to do would be to divide the whole equation by k. So those are going to go to about 1. And then we divide the whole equation by I hat. And so I've got 0 equals q1 over x1 squared minus q2 over x2 squared minus q3 over x3 squared. And what we're solving for is x3. So let me subtract this term across. So I get q2 over x2 squared minus q1 over x1 squared is equal to minus q3 over x3 squared. I guess it would have made more sense to add the other one across. Because now what we can do is, bless you, take the negative of everything. Yeah, that makes more sense. Now what we need to do is multiply by this quantity on both sides, and we need to divide by this quantity on both sides. And so we get x3 squared is equal to q3 over q1 divided by x1 squared minus q2 over x2 squared. And then we need to take the square root of both sides. But remember, taking the square root of both sides means that we get two answers. x3 is going to be equal to plus or minus the square root of q3 divided by q1 over x1 squared minus q2 over x2 squared. And it turns out that what you get for this last answer is that it's going to be plus or minus 2.38 centimeters after you plug in all the values that are given to us in the problem. And again, we now have to rationalize by inspection, since the mathematics gave us two answers, plus or minus 2.38 centimeters. Which one is correct? The positive one, because we already reasoned out what directions things had to go based off of the physics. So the math can usually only get you so far. You have to take the physical nature of the problem into account to figure out the rest. And just like we said, it ended up being closer than either of the other two charges to counterbalance the fields created by those other two charges. Grayson? What do you mean? I'm so sorry.
So how would we choose why this is positive, why this is, or if it's negative, the final answer?
So how do we know that the final answer is positive or negative? Again, this whole solution precipitated on the fact that we need to have a positive charge to the right here such that the field created by that charge at the origin is to the left to counterbalance both of these. Good question. It took us a long time to get here. Bill and then Andrew.
Could you not have a negative charge to the left?
You could add a negative charge to the left, but the problem said, where should a third charge that's plus 6 microcoulombs be added? Andrew?
The question asks, say, the magnitude of the charge, the magnitude of the field. Is the negative included in that, or is the direction included in that magnitude, or is it just the value itself?
If it had just said you have a 6 microcoulomb charge and you just know the magnitude of it, then you'd have to take into consideration that it could be positive or negative, and we'd have to keep both solutions. Where the positive would correspond if the magnitude charge was positive, and the negative solution would correspond if the charge was negative. Okay, yes.
Can you explain your logic on how you know that 0 has to equal the sum of the other 3 electrons?
Because it says that we want the electric field at the origin to be 0, right? So the electric field at x equals 0, which is my origin, equals 0, just based on what we're trying to solve for here, and that leaves me with the single unknown x3. They could have made this problem infinitely harder and said if the field at the origin was 1 Newton per Coulomb, because then we wouldn't get all of these nice cancellations here, right? You'd have to carry around your factors of k, you would have to carry around this extra term here, and you'd get a much less elegant solution inside your square root. Bill?
I know we can't fill out, but what is K?
K is the Coulomb constant. K is equal to 8.988 times 10 to the 9. And that's in Newton meters squared per Coulomb squared. Also on your equation sheet. I would encourage you to look at this problem, the third problem on this set, on Canvas after class. This takes exactly what we just did into 2 dimensions. So now we have to keep up with the x hat and j hat components of everything. But I have the solution posted online. Man, I would love to do both of these, and we are very far behind. Let me just show you how to set up this one, and then we can go about figuring it out. And then I have one problem down here that's pretty straightforward about dipole moments. So I would encourage you to look at this one as well. We're going to skip the 3rd and 5th one in this set. And this one we're just going to set up. An electron starts at the position shown with an initial speed v0 equals 6 times 10 to the 6 meters per second at 45 degrees with respect to the x-axis. The electric field is in the y-hat direction. And so if the electron eventually gets here, just drawing it where you can see it a little bit better, the force has to be in the opposite direction. So you can see that just like in our projectile motion problems back last semester, we've got a downward force, something being launched upward. So this is projectile motion. The electric field has a magnitude of 3,000 newtons, or 3.5 times 10 to the 3 newtons per coulomb. The black lines in the figure are charged metal plates. On which plate and at what location will the electron strike? And so with this, it's actually convenient to say, okay, well, delta y is equal to, let's see, v naught y times t minus, in this case, since the force is downward, minus 1/2 times the acceleration in the y direction, or let's say plus, and then we can take into account times t squared, or delta y is equal to v naught times sine theta, where 45 degrees is theta, times t, plus 1/2 times minus for the acceleration is going to be, let's see, we've got F is equal to QE, and that's equal to MA. So we've got A is equal to QE over M. So we've got minus Q times E over M times T squared. But the problem is we don't know what T is. So the other thing that you could take into account is that Vy squared is equal to V naught Y squared minus 2 times QE over M times delta Y. And what you would want to do to solve this problem is figure out, using this equation, how high does the electron go between the plates? Right? So how would you figure out how high the electron goes between the plates using this last equation that's starred on the board there? Think back to your time in Phys 1. Yeah, you're solving for delta y using the starred equation. How would you solve for delta y? Like, we know what V naught y is. We know the charge, we know the electric field, we know the mass. What I'm ultimately asking you is, what is Vy, the left term there? What is that term when it's at its maximum height? 0. Yes, at its maximum height, that value is 0. And that would give you that Y max, in this case, the maximum height that this thing reaches is going to be equal to 1.01 centimeter. Okay, so the highest this thing gets is 1.01 centimeters. I'll leave you to fill in the details afterwards. So if it's 1.01 centimeter, does it strike the top plate or the bottom plate? The bottom plate, exactly. So it strikes the bottom plate. Okay, now we need to know in what location, how far down, or how far in the x direction does it strike the bottom plate? How do we solve for that? How do we figure out it strikes the plate here at this distance, x? It goes right there. No, I wasn't erasing it. I was showing you where it hit. How do we figure out that distance x? Jacob. Okay, so we have to take into account that the displacement x is equal to v naught x times t plus 1/2 ax t squared, but as he correctly reasoned, there is no acceleration in the x direction, so we're just left with that this is v naught cosine theta times t. Good. Okay, the next logical question is, how long does it take for it to strike the bottom plate? Well, I don't know. It's not given in the problem, so how do we calculate it? What? William? Yes, when it strikes the bottom plate, delta y, when it strikes this plate, is equal to 0. Good. So, if I take this equation right here for delta y equals 0, then that would end up giving you that the time that it takes for this to occur is going to be equal to 11.49 nanoseconds. And then that gives you delta x based off of this 5 million meters per second velocity is equal to 4.06 centimeters. I've given you all the puzzle pieces. Before you look at my solution, as you're looking at this after the fact, try to consider and take a look yourselves and see if you can fill in those gaps yourself and meet those mile markers along the way. Okay, any questions? I specifically went through that one because I know that's drawing upon things that you might have already brain dumped from the first semester, unfortunately. Okay. Let's go back here and exit out of this. I would love to go to our next. Oh, no. That was the correct. Whoops. That was the correct. We needed to continue on. And at least do this, and we'll start with problems here next time to discuss how to do electric fields of continuous charge distributions. And you'll see my subtitle there, Hooray Integrals, right? This is where calculus-based physics really starts, the rubber starts hitting the road here, right? Because if we're talking about something that's discrete, well, when you want to take multiple discrete things and put them together, we call that a sum. But if something is continuous, well, now we're taking the sum over infinitely small things an infinite number of times. Well, if we're going from discrete to continuous, we're implicitly talking about doing an integral. Like, yay, integrals. From Coulomb's law, recall that for a point charge Q sub I, the electric field at the point P is calculated as KQ over R squared times R hat. That's what we just wrote on that second problem where we were trying to find the electric field was 0 at the origin. And so how can we calculate this electric field over a continuous charge distribution? Well, instead of adding up Q sub I, that means we're going to have to integrate over a differentially small amount of charge. So continuous charge distribution of charge, continuous distribution of charge, a differential component of the electric field. So you can see from this little yellow blob here, the amount of differential electric field contributed at point P from this single point in the blob, the yellow blob, which is just a differentially small amount of charge Q. And I apologize, again, I didn't get this slide edited. I use big Q here and little q here, but I'm talking about the same amount of charge. So you can write it in your notes. Everywhere you see a D little q, it should just be a big Q. So I've got the differential amount of electric field is going to be K times dq, d big Q, over R squared times R hat. And we must integrate over that dq to figure out what the total electric field is at point P. So we're taking the integral of K dq R hat over R squared. An integral that is easy to write down, but then becomes a little frustrating to calculate. And I'm going to forewarn you that when we get back on Tuesday, I'm going to solve 3 example problems from your book. And I'm saying not problems at the end of the chapter, 3 problems that are listed as example problems in the text of your book. And I am going to do the full integral treatment just so you know how this stuff works. I shouldn't say forewarn you, encourage you, I guess I should say, that in your book, all we will deal with are symmetric charge distributions that are also uniform charge distributions. And when that happens, all of a sudden these really complicated integrals that we're going to work through become very easy to solve geometrically. And your textbook solves the problem with the geometric simplification. So I don't want you to get scared of big integrals on Tuesday of next week. In fact, go ahead and look at my slide deck from next week and my problem set from next week. You'll see where those example problems come from in your book, and you can go ahead and comfort yourself that there are easier ways to do this, and we'll do some of those as well. But I want you to be convinced on Tuesday that the geometric approximation or geometric formulations that we're going to start using exist just because the integral works. The way the integral works is that we assume that dq, the differentially small amount of charge, can be three different things. For a line distribution of charge, it is equal to lambda times a differential length. For an area, it's equal to sigma times a differential area. And for a volume, it's equal to rho times a differential volume. Lambda, sigma, and rho, if y'all are trying to start a new fraternity or sorority on campus, there you go, lambda, sigma, rho. Lambda, sigma, rho are all line, area, and volume charge distributions. Lambda, sigma, and rho are all linear area and volumetric charge distributions, respectively. Jacob? Lambda can be used for wavelength. Yes, the problem is we have near infinite number of variables in physics, and we have non-infinite Greek and English letters to choose from. Occasionally, I did see a paper where they ran out of English letters and Greek letters for their variables, and so they pulled in the Hebrew alphabet. So that was fun. Because why not? Now, what's going to be nice about the integrals that we're doing is that in your class, in this class, lambda, sigma, and rho are all constant. Or uniform. It's going to say it's 1 nanocoulomb per meter, or 1 microcoulomb per square meter for lambda and sigma respectively. You're like, okay, then why are you going to all the trouble to show us this? Well, if you have to take electricity and magnetism or electromagnetism for physicists, or you end up going into graduate school with all of this stuff, you don't get to assume that these are continuous are uniform symmetric charge distributions. And then the integral becomes crazy difficult. The differential elements, at least in Cartesian coordinates, are really well behaved. A differential volume, if you look at this cube here, is just going to be, well, the differentially small amount of volume here is going to be dx times width, dy, times height, dz. So volume is dx, dy, dz. Woohoo! The differential areas are more frustrating to deal with because now I have an area that is pointed out along the x-axis, one that's pointed up along the z-axis, or one that's pointing out along the y-axis. I think I got y and x mixed up. Out along the x-axis, out along the y-axis, or out along the z-axis. And let's take, for example, just this one that is pointed in the x direction. So this front face here. The front face has a differential length of dy and a differential height of dz. So I would have here the front differential area is going to be dy times dz times the x hat direction. The top face is going to be dx dy in the z hat direction, and the right face is going to be dz dx in the y direction. I can already tell you, at least in the problems we're going to solve, you're not going to have to treat each of the three different faces independently of one another. The problem is going to be oriented such that you have a plate in the z equals 0 plane, which would be the xy plane here, and then you've got one at the z equals 5 plane up here. So you have two plates that are horizontal. Well, in that case, the only differential area you're going to need is going to be this one pointed in the z direction, so you're just going to be integrating over x and y respectively. Again, I know this feels like a lot. We're going to do some of these. I'll walk you through it. But the main point that I'm showing you all of this is just to show you that when we make the geometrical formulation, it's not just magic. It doesn't just pop out of nowhere. For cylindrical coordinates, you get dv is equal to rho, d phi, dz. And you get each of these differential areas. And then when we wrap up, we're going to get the spherical elements as well. I'm going to put the spherical ones up there, and then I can come back afterwards. The spherical element is really fun. But again, don't lose your cool. I know I have 5 days before I see you again. We'll get there, I promise. Until then, keep in mind, comfort yourselves and know that the level of difficult calculus that we're going to be doing has geometrical counterparts that are very easy to use. And I will see you on Tuesday.